In this video, we're going to take a look at a special type of a sequence, which is called an arithmetic sequence. So our definition here says that an arithmetic sequence is a sequence in which consecutive terms have a common difference, and we call that common difference D. So let's shed some light on this definition and see if we can unpack this and understand what it means by looking at these two examples of arithmetic sequences. My first example has the terms 3, 5, 7, 9, and 11. So remember, we're all about looking at patterns here. And in this example, you'll see that we're adding 2 repetitively to get from one term to the next. So if I were to ask you what the next term was, you could tell me to add 2 to 11. So the next term would be 13. So in this case, the common difference, which we're using D to denote the common difference would be 2, since we're adding 2 repetitively. Now let's go back to this definition, a sequence in which consecutive terms have a common difference. So consecutive means we're looking at 2 terms that are right next to one another in the sequence. So for example, if I were to take the second term, which would be denoted a sub 2, and subtract the first term, a sub 1. In this example, the second term is 5, minus the first term, which is 3, and you see you get the common difference of 2. So we're subtracting 2 terms that are right next to one another. Let me do that again just to show you that it does indeed work for any 2 terms that I pick that are consecutive. So let's say we take the third term, a sub 3, minus the second term, a sub 2. The third term is 7, minus the second term, which is 5. And indeed, that gives us again that common difference of 2. So we can identify an arithmetic sequence by looking for a common difference. If we have a common difference, then we know that the sequence is arithmetic. Look at the second example. Here we're going from 18 to 15, so we're actually decreasing this time. So we're not adding a value repetitively, we're actually subtracting. In this case, subtracting 3. But remember, when we say we're subtracting 3, we really could also write that as adding negative 3 repetitively. So we really are adding a value every time, we're just adding negative 3. That's the same as saying we're subtracting 3. So in this example, our common difference would be negative 3. And if we continue subtracting 3 repetitively, we'll get additional terms in this sequence. So once again, let's show how we can subtract consecutive terms to verify this. If I were to take the third term minus the second term, the previous term, in this case the third term is 12, minus the second term, which is 15, and sure enough, that gives us that common difference of negative 3. And if you wanted to check that again with 2 other terms, you can pick any 2 terms that you want that are consecutive right next door to each other. So on this one, what if we chose these last 2 terms here? So let's see, this would be, the first term is when n equals 1, then we have n equals 2, 3, 4, so this looks like n equals 5, and n equals 6. So that would be the 6th term minus the 5th term. The 6th term is 3, minus the 5th term is 6, and indeed you see that common difference again of negative 3. So what I'm demonstrating here, where you subtract the consecutive terms, it's really not usually needed on examples like these 2, where it's pretty obvious what the common difference is. But if you're dealing with some decimals or some complicated looking fractions, you might find that subtracting the 2 terms is actually an easier way of figuring out your common difference, just when it's not obvious. So now let's work on finding the nth term, the general term of an arithmetic sequence. So finding the nth term means I'm looking for essentially a formula or a general rule. So you can think of this as a general rule or a general formula that's going to generate all of the terms of a sequence. So for example, if I want to know the 100th term, then I just want to be able to plug 100 into a formula and know the 100th term. I don't have to actually find all 99 of the previous terms. I just want a nice formula here. So let's look at this numerically. And numerically means we're going to make a table. So if n is equal to 1, that means we're looking at the first term of a sequence. Now I'm not going to use the two examples above. I want to generalize. What would we call the first term of a sequence? So in general, we call the first term a sub 1. Now let's think about how we would get to the second term. I know I could call the second term a sub 2, but I'm not going to do that in this case. Instead, I want to look at the pattern. So to get from the first term to the second term, if it's an arithmetic sequence of numbers, we know we take the first term and we're going to add a common difference, whatever that common difference is. So my second term could be written as a sub 1 plus d. Now let's move on to our third term. We're going to do the exact same thing. We'll take the second term and we are going to add another d. So that means the second term, which was a sub 1 plus d, now we add another d to that. Well, this becomes a sub 1 plus 2d. So the third term of the sequence could be written as a sub 1 plus 2d. Now let's do that one more time for n equals 4. If we're looking for the fourth term of a sequence, we could take the third term and add another common difference. So if the third term was a sub 1 plus 2d, and now I'm adding another d, now I have a total of a sub 1 plus 3d. And at this point, we want to step back and see if we can generalize. Can we establish a pattern? So I'm going to write dot, 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 because I know I could continue this process on, and let's just continue it on for any term. We'll mark that as n. So look at the right-hand side, and let's see what all of these entries have in common. Notice that we are always starting with the first term. So it's always a sub 1, and then it's plus something. So our generalization here will be, let's start with the first term, and we're going to add something on. And now let's look and see what we're adding on. We're always adding on some amount of d's. In this case, I added 3d. In the previous case, I added 2d. In the case before that, I was really adding 1d. And in the original case, you could even think of this as adding 0d if you wanted to. So the question is, how does the number in front of d, or the coefficient of d, how does that relate to the value of n? When n equals 4, we added 3d. When n was equal to 3, we added 2d. When n was equal to 2, we added just 1d. And even for n equals 1, we added 0d. So I hope you can see that the coefficient, the number in front of d, or the number of d's that you're adding, is actually 1 less than n. So we're adding n minus 1 times d. And this is our generalization, or this is our general rule, our general formula that will get us any term in an arithmetic sequence. So we'll write a sub n is equal to the first term, which is a sub 1, plus n minus 1 times d. And this is our rule that will allow us to write a formula for any sequence that's arithmetic. So let's just go back to this very first sequence just to show that this rule is going to work. Our first sequence, which was 3, 5, 7, 9, 11, and so on. We had already established that our common difference was 2. So if we use this formula that we just came up with, the first term of the sequence was 3. We would have plus n minus 1 times d, and d would equal 2. So if you were to distribute, this would turn into a sub n is equal to 3 plus 2n minus 2, which is really the same as a sub n is equal to 2n plus 1. So this would be the general rule that would generate the sequence of numbers 3, 5, 7, 9, and 11, which is an arithmetic sequence.